and we're now recording. So we'll put the roll book aside here for now until the other guys come in. We're in Chapter 2, Matrices, Section 2.2, which is titled Properties of Matrix Operations, and we're on the very last example on page 58. Okay, example 10, and it is a product of a matrix and its transpose. So here's how we'll be beginning this one. Here is a matrix A. Get my pen to show up. There it is. Matrix A. And now it goes straight to text. I don't know. Wait, hold on. Let's see. Who was this coming in? I clicked yes before I saw his name. It's Jesus Miguel. Okay, so we have the top and the bottom of the alphabet. We're waiting on the middle. That would be James. Hopefully he'll get here soon. All right, Jesus Miguel, we're in Chapter 2, Matrices, Section 2.2, which is the Properties of Matrix Operations. On page 58, the very last example in the section, that's example 10. That's what we're getting ready to do, and I need to scoot the two of you over, and me, just a tad, so I have a little more white space to work. Okay, so here's where we were right before you came in. If I can get my pen to show up here. Okay, there it is. Here is matrix A. 1, 3, 0, -2, -2, -1. Okay. For that matrix A, find the product of A times A transpose. So I guess what we have to do first is figure out what A transpose is. Can anyone tell me what A transpose is? What will be its size? Let me back off one. What's the size of A? That's an easy question. What's the size of A? Something by something. Anybody? 3 by 2. So what would be the size of A transpose? You exchange the rows and columns. So it'll be a 2 by 3. So what would be the elements in it? 1, 1 would be
1, 0, 2.
1, 0, -2. Next.
3, -2, -1.
Perfect. Okay. Now we're going to do the product of those two. A times A transpose. Now, what size will that be? We already said A was a 3 by 2 and A transpose was a 2 by 3. The first question we have to ask ourselves, can we even multiply those? Yes, we can, because the inner numbers are the same. Wipe them out, and that gives the size of A times A transpose to be a 3 by 3. See why that's true? So therefore, A times A transpose is going to be a 3 by 3. 3 columns, 3 rows. The first entry here, first row, first column, will be the first row of A times the first column of A transpose. And what would that be? One times 1 is 1, plus 3 times 3 is 9. 1 plus 9 is 10. Correct? Okay. The 1, 2 entry here, first row, second column, will be the first row of A, second column of A transpose. That would be 1 times 0 is 0. 3 times negative 2 is negative 6. Correct? The 1, 3 entry here, first row, third column, will be the first row of A, third column of A transpose, and that would be a 1 times a negative 2, plus a 3 times negative 1 is negative 3. That would be a negative 5. Correct? Okay. The 2, 1 entry here, second row, first column, be second row of A times the first column of A transpose. That's a 0 times 1 is 0, plus a negative 2 times a positive 3 is a negative 6. The 2, 2 entry here, second row, second column, will be second row of A, second column of A transpose. 0 times 0 is 0, and then minus 2 times minus 2 is positive 4. Correct? The 2, 3 entry here will be second row, third column, second row here, third column of A transpose. And that would be a 0 times a negative 2 is 0, and negative 2 times a negative 1 is a positive 2. Okay? The 3, 1 entry here, third row, first column would be third row of A, first column of A transpose. Negative 2 times 1 is negative 2, plus a negative 1 times 3 is negative 3. That comes out being a negative 5. The 3, 2 entry here, third row, second column, will be third row of A, second column of A transpose. It would be a negative 2 times 0 is 0, plus a negative 1 times negative 2 is a positive 2, so that's a positive 2. And then the 3, 3 entry here, third row, third column, will be third row of A times third column of A transpose. That would be a negative 2 times negative 2 is positive 4, plus a negative 1 times negative 1 is positive 1. That would be a 5. Now, time out just a moment here. Do you notice anything a little bit special about this matrix? We've hit the concept before, not very hard, I think, or maybe we haven't hit it. I think we have. But what I want you to notice is these two entries are exactly the same, these two are exactly the same, and those two are exactly the same. So if you eliminate your main diagonal, which has no relation to anything, just eliminate that, then the others are reflections of each other across that main diagonal. We call this a symmetric matrix. That's a symmetric matrix. Okay? Now, I think we've hit that before. Now, and the reason it's symmetric, if we did the transpose of this one, you would get, and this is actually the definition of a symmetric matrix, it's equal to its own transpose. Okay? If you did the transpose of that, you'd have a 10, and then you come down here and you have a minus 6. Come down here, you have a minus 5. Transpose next would be this column, a minus 6, 4, 2, and then the third row would be the third column of this one, minus 5, 2, 5. And that's exactly equal. This is A. Goodness gracious, this pen is writing really poorly. A transpose, that's what it's supposed to be, transposed, the transpose of that one, and they're exactly equal to each other. That means they are symmetric matrices. If a matrix is equal to its transpose, then it's a symmetric matrix. Guess what? All symmetric matrices have to be square. Otherwise, they wouldn't be equal to the transpose. Okay. Now, a question they didn't do, and I think this is on the remark at the side, let's see what happens if we do A transpose times A. Okay. I'm trying to find my pen. There it is. So let's rewrite A over here. That's a 1, 3, 0, negative 2, negative 2, negative 1. Just rewrote A over here. And now we're going to multiply A transpose times A. And what does that equal? Oh, what size is it? This is a 2 by 3. This is a 3 by 2. Wipe out the middle values and you get a 2 by 2. So this is a 2 by 2 matrix here. So obviously it's not the same as A transpose or A transpose, because they're completely different sizes. This is a 2 by 2. Okay, blank, 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 blank. To get the first entry here, the 1, 1 entry, let's multiply first row of this by first column of that. Okay, so it'd be 1 times 1 is 1, plus 0, plus 4 is a 5. 1 plus 4 is 5. The 1, 2 entry here would be first row here times second column here, and that would be a 3 plus 0 plus 2. 3 plus 2 is 5. I hope I'm doing this right. Then the 2, 1 entry here would be second row here, first column there. That would be 3 plus 0 plus 2. That would be a 5. Okay, 2, 2 entry here, second row here, second column here. A 9 plus 4 plus 1, that would be 13, 14. That's also a symmetric matrix. These two off-diagonal entries are equal to each other, corresponding to each other. There's only one. So yes, that's also a symmetric matrix, because if you did A transpose times A and then do the transpose of that, that would be a 5, 5, 5, 14, same matrix. So it's also symmetric. All right, there is another blurb at the bottom of page 58. And this is talking about information retrieval system, such as internet search engines. Guess how they do these? Matrices. Okay, everything they do in here is showing us how you apply matrices. Now, what's the most famous search engine probably in the world? Who came out with it? It made that product what it is. I'm using it right now. Not directly, but indirectly. Google. Google came up with a search engine that beat all the others to a pulp. Okay? No one else was close to the rapidity, the efficiency of everything of Google's search engine, and it is still a tightly kept secret. Probably more tightly kept than the formulation for Coca-Cola or something like that. It's completely, others have tried to duplicate it. I don't think anyone's ever come and exactly duplicated it. It is an incredible, guess what they used? linear algebra. Okay, powerful, powerful tool. All right, enough of that. If you want to write on a paper topic dealing with information retrieval or internet search engines or something like that and how they relate to linear algebra, good paper topic. Okay, homework exercises for 2.2 would be any of the odds 1 through 5. They're all at Calc Chat, also in the back of the book. Any of the odds 7 through 11, they're all at Calc Chat and in the back of the book. 13's in the back of the book and at Calc Chat. 15 through 21 are at Calc Chat. 23's at Calc Chat. 25's at Calc Chat. 27's at Calc Chat. 29's at Calc Chat. Any of the odds 31 to 35 are at Calc Chat. 37's at Calc Chat. 39's at Calc Chat. Either 41 or 43 are at Calc Chat. Any of the odds 45 to 47, either 45 or 47 are at Calc Chat. They claim you might need a little assistance doing 47 because it's such a big matrix, but I think you could still do it. 49 or 51 are at Calc Chat. 53's at Calc Chat. 55's at Calc Chat. It's a true-false. 57's at Calc Chat. 59's at Calc Chat. Any of the odds 61 through 69 you're welcome to do if you'd like. They are proofs. Some of them are guided proofs, some of them are just proofs. Especially if you're a math major or in some major that will be doing a lot of proofs, you may want to do some of those. They're usually fairly easy. They are at Calc Chat, so you can use those as cues to figure out how to do them. Either 71 or 73 are at Calc Chat, and then some more proofs. Any of the odds 75 through 79 are at Calc. At least 75 and 77 are proofs. 79 is another pretty hefty matrix that says you might need graphing utility. That finishes 2.3. Any questions on 2.3? All right. I'm sorry, 2.2. Okay, I turned the page and I was reading. We're going to 2.3, and the title of this one is the inverse of a matrix. Okay, we'll first tell you what an inverse is, how you find it, and then some of the properties of inverse matrices, and then we'll use inverse matrices to, guess what, solve systems of linear equations. Okay, so here's how we're going to begin. I'm going to clear the screen. Does anyone need this up a little bit longer? I take that as a no. Now, we still haven't seen James, have we? Let me make sure he's not in the waiting room. No, he's not. Okay. Now, excuse me, let me get a drink of water. I've been talking almost nonstop since 8:30 this morning, so. Now, back in section 2.2, we discussed some of the similarities between algebra of real numbers and the algebra of matrices, and we looked at the properties of matrices and how they related and stuff. This section further develops the algebra of matrices to include solutions of a matrix equations involving matrix multiplication. Okay, we've had that somewhat. To begin, let's consider the real equation that goes like this. Simple equation. AX is equal to B. Now, how do we solve that? We isolate the x, which means we divide both sides by A, which is basically the same as multiplying by the multiplicative inverse of A, which is 1 over A, okay? And that's what gives us the value of x. That is your B times the reciprocal or multiplicative inverse of A. Okay. Now, sometimes we write that as B times A inverse, 1 over A. That's the symbol we use when we're talking exponents. 1 over something is to the negative exponent. Now, they actually wrote it this way, and it doesn't really matter with real numbers, but it will matter in this. The number A is the multiplicative inverse of A because it's reciprocal of A. If you multiply A inverse, which is 1 over A, times A, you get the multiplicative identity, which is 1. Okay? Identity element for multiplication. So this leads to the definition of the inverse of a matrix. Now, I know I've asked this question several times before. Do both of you have access to your books right now, or when you're watching the Zoom thing, does that prevent you from looking at your book at the same time? Any of you have that issue?
It doesn't prevent me, but it's just, I struggle more because it's small.
Right. Okay, exactly. So let me go on, and I think that I'll probably type this one in just because my writing is so scratchy on here. It might take me a little longer, but I think I'll go on and type this in. Okay. Okay. Set my pen down for a moment, put the pad out of the way for a moment, and let's get to typing. Okay. An n by n matrix A is called invertible. Well, that means it's able to be inverted. Now here's another word for it. Okay, this one doesn't make as much sense now. Somewhere in the future you'll probably see why they name it this. Another name for it is non-singular. Same meaning as invertible. Non-singular. When there exists another n by n matrix B such that AB, the product of AB, is equal to BA. Time out a moment here. Remember we said most of the time multiplication of matrices is not commutative. The AB most of the time is not equal to BA. But this is a very special same size matrix, square matrix, has to be square, B, that makes that commutative multiplication mode. And not only are they equal, but they're equal to I sub n. Now I can't do a subscript here, but that means sub n. Where I sub n, I hope you remember, is the identity matrix of order n. Now what is an identity matrix? One's down the main diagonal, zeros everything else, everywhere else. Okay, n rows, n columns. Okay. The matrix B that makes that happen is the, and they're going to put in parentheses here, and most of the time we'll leave off the word multiplicative whoops, wrong thing, multiplicative inverse of A. A matrix that does not have an inverse is non-invertible. or, of course, singular. Okay. Now, there's our definition. I'm going to stretch it out some, so I think it should be easier to read. Certainly. Okay. I hate that. Let's see what I think I'll do here. Do the same thing they did in the book. Okay. An n by n matrix A is invertible or non-singular when there does exist another n by n matrix, same size matrix, have to be square, both of them, B, such that AB is equal to BA, and not only are they equal, but they're equal to the identity matrix of that same size, I sub n. Where I sub n is the identity matrix that's of order of n, meaning n by n, because it always is square. Identity matrices are always square. That matrix B is the multiplicative inverse of A. Most of the time we'll just say the inverse of A. A matrix that does not have an inverse, that's an inverse, not and inverse, is called non-invertible, that makes sense, or the other word, singular. Does not have an inverse. Now, I'm sorry, I'm looking at the wrong proof. I was going to say the proof they show is not for this. Okay. Now, a regular rectangular matrix like that 3 by 2 or the 2 by 3 we were dealing with before can't possibly have an inverse, because inverse matrices with inverses have to be square. So if it's not a square matrix, hang it up. There is no inverse. Don't even try. Okay. Because if you did have an m by n where m was not equal to n, then B would have to be an n by m in order to multiply them, and then you would come out with a matrix size m by n. But if you did them the other way and did B times A, then you would wind up with an n by n. And we said those are not the same size. So obviously that cannot happen. Non-square matrices cannot have inverses. Okay. Now, one more theorem here. So let's come down here and do the next theorem. Okay. This is theorem. Oh, that was a definition. Here's the theorem. If A is an invertible matrix, then its inverse is unique. It can't have two inverses that are different from each other. Okay? The inverse matrix, the inverse of A is denoted by, I can't type this either, I wish I hadn't started this. A, and I can't do a superscript to the -1. That should be a superscript. Okay? That's what we call the inverse of a matrix. I need a period after that. Okay. Now, whoa, if I could spell matrix right. Okay. Now, let me write this the way it's supposed to be. So let's go to my draw mode here and get my pad back here and my pen back here. This is what the inverse of a matrix is denoted by, if I had the right end of the pen, it's a to the minus 1. Now, just like we said, little a to the minus 1 was the multiplicative inverse of the number a, we say capital A to the minus 1 is the multiplicative matrix inverse of matrix A. Now, that's where things fall apart. Little a is 1 over a, 1 over little a. Capital A inverse is not 1 over capital A. Nowhere close. We don't even mess with trying to define matrix division. I don't know that there is such an animal. So, do not interpret this to be that. It's more like the inverse of a function. If you think about a function of its inverse of its inverse function would produce the value x, okay, always, and f inverse of f would produce the value x. Now this is a composite, but this is a times a inverse produces I, okay. They both a and a inverse must be square matrices, same size, dimension n, and they produce, when you multiply them, the identity matrix. A lot like here, this produces the number 1, it produces the identity matrix, but in some senses that's a little bit more like an inverse function of itself, of the function, will produce the value x. It's not quite the same, but it's sort of an integrate in between the two. Now they do a little proof here, and it's a pretty easy one for this one. If A is an invertible matrix, that means that there is an inverse. Let's call it A inverse, okay, and the product of those two has got to be I. You know that, okay. So that inverse we're going to say is unique. So let's, rather than call it I, A inverse, let's be a little more generic about it and call it B. So if B is going to be the inverse of A, which would be A inverse, but let's call it B. Okay. Now, what if there was another matrix that was, oh, and by the way, that's also B times A. That's also I. That's the other thing about it. A, B is equal to B, A, and that's equal to the inverse, the identity matrix of the same size. Now, what if there was another matrix? Not a unique matrix, another matrix C that was equal to I, and this is also equal to CA. Okay? What if there was another one? The B is not equal to C. There's another matrix out there. Well, if this were the case, and this is what they do a lot, if AB is equal to I, we'll just take this part right here. AB is equal to I. You know it has to be. If that's your inverse, it is. And let's just multiply this by the matrix C. That means you multiply I times C. Okay? Now, because you can associate differently, this could be CA times B would equal to, and C times I is just C, because it's an identity matrix. Okay? Now, we said here that C is also equal to I, right? So this would be I here. CA would equal I, we said right here. That times B, they're saying, is equal to C. But this says I times B, you know that's equal to B. So this says B has to equal C, and originally we said B was not equal to C, so we produced a contradiction, so that means that C and B must always be equal to each other. There is only one a unique inverse matrix. Okay? So the inverse, A inverse of matrix A is unique. You can call it the inverse of A, and then from here on we will call it, wherever my pen, there it is, A times A inverse is the same as A inverse times A, and both of those products are your I, where I sub n, whatever the dimension of A is. Okay. All right, I think we beat that to death. Let's go to example 1. Can I clear this slide? Whiteboard. So I'll erase my whiteboard here, and let's do example 1. I think I'm going to have to put it in my lap here. Here's matrix A. -1, 2, -1, 1, and here's matrix B. -1, -2, 1, -1. Okay. Now, what we're asked to do is to show that B is the inverse of A. And of course that would imply that A is the inverse of B as well. Okay? Well, how do you show this? You multiply them together. So AB would then be obviously a 2 by 2, because both of those are 2 by 2s, and the first row, first column here would be, let's see how we're doing on time. We go till 12:45, right? Yeah. Just about all my classes in different times, so I have to stop and remind myself. So to get the 1, 1 entry here, first row, first column here, we do first row of A times the first column of B. That will be a -1 times 1 is -1, plus 2 times 1 is 2, -1 plus 2 is 1. Good so far. To do the 1, 2 entry here, first row, second column, we do first row of A by the second column of B, and that would be -1 times -2 would be a +2, plus a 2 times -1 would be a -2. Whoops, that's a 0. Well, good so far still. The 2, 1 entry here, second row, first column, would be second row here, first column here. It would be a -1 times 1. -1 plus 1 is 0. Hey, 3 out of 4 is not bad. But let's see if we could do the fourth one. The 2, 2 entry here, second row, second column. That would be a +2 minus 1, sure enough, is a 1. Okay, now technically that should be enough, or you would think it would be enough, but let's confirm it by rewriting A over here. Yuck. To be -1, 2, -1, 1. And let's multiply and see what BA produces. Again, it's going to be a 2 by 2. The 1, 1 entry here, first row, first column, so first row of B times the first column of A, B1 times the -1 is -1, plus 2 would be 1. Yep. 2, 1 entry here, 1, 2 entry here, first row of B, second column of A, would be 1 times 2 is 2, minus 2 is 0. Okay, excuse me just a minute. My throat is going on me. Sorry about this. Okay. Whew, man. The 2, 1 entry here, second row, first column, second row of B times the first column of A would be 1 times a negative 1, which is negative 1, plus a negative 1 times negative 1, which is plus 1. That sure enough adds to 0. And then the 2, 2 entry here, second row, second column, that would be 1 times 2 is 2, plus a negative 1 times 1 is minus 1. Sure enough, that's a 1. So yes, both the A times B is the identity matrix and B times A is also the identity matrix. Okay, so we've done example 1. Let's move on to example 2. All right. I think we're going to need to clear. Anyone need this a little longer? Okay. Let's do example 2. Find the inverse of this matrix A. Now this is going to be a long, messy process, but hopefully it will lead us to an idea of how to make it a little more reasonable. So here's the matrix A. Not the same one we had before, unfortunately. 1, 4, negative 1, negative 3. Now we'll later learn easier ways to do this, but here is at least a brute force way. Let's just say that its inverse is going to be B, but we don't know what B is. So let's name it B11, B12, B21, B22. You know it's got to be a 2 by 2 matrix, so there's a 2 by 2 matrix. And we're going to say that the product of these two matrices has to equal I. So 1, 4, negative 1, negative 3 times B11, B12, B21, B22 has got to equal the 2 by 2 identity matrix. 1, 0, 0, 1. If that's the inverse, that's got to be true. Got to. No doubt about it. Okay. Well, let's do the multiplication and see what we get. We get 1 times B1, 1, plus 4 times B21. So B11 plus 4 B21 has to equal 1, right? This by that has to equal that. Okay, let's do the 1, 2 entry. This one times that one, so that will be B12, I'll start to write it backwards, plus 4 B22 has to equal 0, because that's the entry. Then the 1, 2 entry here, that would be minus B11 minus 3 B21 has to equal 0, and the 2 entry here would be minus B12 minus 3 B22 has to equal 1. Okay. Now, we have 4 equations, 4 unknowns. We could set it up and do a Gauss-Jordan or a Gaussian elimination. And I guess that's what they do, except we'll notice this. This is just 2 equations, 2 unknowns. This is 2 equations, 2 unknowns. So let's just do them separately. Okay? The first one is B11 plus 4B21 is equal to 1. And the third one is minus B11 minus 3B21 is equal to 0. Well, if you add these together, that goes away, and you get B21 is equal to 1. Hey, I can handle that. So B21 is equal to 1. So this will be value 1. Okay, let's put that back into, say, the top equation, and that would give you, if I could find up, there it is, B11 plus 4 times 1, that's 4, is equal to 1. So B11 is equal to negative 3. So B11 is negative 3. Okay? Well, I'll write it there. Negative 3, I'll write it there. Okay. Now, let's do the same with the second pair of equations. Let me do that here if I can. B12, get out of there. I don't know why that showed up. But let me erase it. So, yuck, the eraser's not coming up. Extraneous marks can be confusing. B12 plus 4 B22 is equal to 0. That was equation 2 here. And minus B12 minus 3 B22 is equal to 1. When you add these two together, that goes to 0, and this gives you B22 is equal to 1. Well, we got this now. Wherever it is, come on, there you are. This is equal to 1. And then let's plug that in here, and you get a B12 plus 4 times B22, and B22 is 1, is equal to 0, and that gives us that B12 has to equal negative 4. So this B12 is, yuck, where are you? There you are. Negative 4. So, what's the inverse? What does that be? A inverse must be negative 3, negative 4, 1, 1. Okay. Excuse me. Get one more swig of water or drink or something here. All right. We have just found the inverse. Now that, so one down here is pretty ugly. That's a 1 here. Okay. And let's see, that's how the book did it too. The x, they called it x. They called it x, the unknown thing. I called it b, they called it x. They still got -3, -4, 1, 1. Same as we did. Now, notice you did have 2 equations, 2 unknowns, 2 pairs of them, made it pretty easy to do. Now, I'm going to take the numbers. No, I really can't. I wish I had more room on my slide. I took up all the room I had. Let me get rid of what I can. Let me go back and get my eraser. Okay. We'll get rid of this. And we already have this, so I'll get rid of that too. Don't really want to get rid of that, so I'll leave it for a moment. Okay, I'll leave that alone for a moment too. I think I'll get rid of this one. What they're going to do here almost looks like a sleight of hand. Oh, I probably didn't want to get rid of that one. I'm going to leave it there. Partly there anyway, because I already erased part of it. Okay. I just need more room to write on this slide. And I want to leave some of it here. Okay. Put this back in. Okay, and I think I'll take that out too, because it's the one sort of nebulous quantity up there. Okay. Now what did we see we had here? If you looked at these 2 equations here, I took out the thing, I'm putting them back in now. You had that basically, notice the coefficients here. This is a 1. Oh, I must have lost this. Yeah. Wait, I lost this one. That's a minus there. That's a plus, minus, plus, minus. Yeah. Okay. Yeah. Okay. When I erased the other, I lost that. Okay. Now what we've got here is, if you look at this carefully, you'll see you got this matrix A, 1, 4, -1, -3, times what I was calling B11, B21, and that was equal 1, 0. Because you did this and this is only deals with 1, 4, -1, -3. That's the A. B1, B11, B21, B11, B21. That's that. And this is equal to this and that. Okay, I think I will erase this one. I'll probably kind of regret it later, but I think we can. We know what that is. Okay. Then my next set from these two was again your A, which is 1, 4, -1, -3, times, this time you're multiplying by B21, B22. No, B12. Yeah, I'm sorry, I wrote that backwards. B12, B22. What does that equal? That equals 0, 1. Okay. Now, if we put those together, okay, let me make sure I do it the same way they did. Since these two parts okay, I'm sort of skipping a step here. If we had done this as equate, well, like I've got here, take these two and just do the matrix equation there, just the coefficients. That was 1, 4, 1, 1, or -1, -3, 0. That would have been this one and this one, okay? And then you solve for that. Well, this one would have been 1, 4, -1, -3. That's these two. And that would have been 0, 1 then. Okay. Well, since these two are the same, what they do is just combine them together and do a 1, 4, 1, 0, -1, -3, 0, 1, and do those all at the same time, do our row reduction, and you'll get exactly that. Okay? Now, the book does a few more words. They can write more than I do. They're just doing that, doing their elimination, just like you did, because it's the same elimination. You're adding those two together. You're doing the same thing there, and that's what you wind up getting. And Kira said she had to go to a doctor's appointment, so she's just taken off. Okay, but then when you do the row reduction of this, you wind up with a 1 here, a 0 there, and then a 1 here and a 0 there. And guess what? When you do the row reduction of this, what it produces is this: 1, 0, -3, -4, 0, 1, 1, 1. Okay? So basically, if you start with your matrix A, augment it with your identity matrix of the right size, I sub n, do your row reduction on this, and when you do your row reduction, you're going to get that identity matrix here in front, and what you have instead of it, you're going to have A inverse. That's what this is. That's what that is. Okay? So that is a shorter method for doing your finding an inverse. Okay, so let me clear this out of the way and type that in for you. Well, I thought I cleared it. There we go. Finding the inverse of a matrix. Okay, by Gauss-Jordan elimination. This time we do Gauss-Jordan. Okay, Let me get my text. Okay. Let A be a square matrix of order n. Means n by n. Okay. First thing you do, write the n by 2n. Now, I don't usually phrase it this way, but that's how the book does. Matrix that consists of A on the left and I'm going to just call it I sub n. That's supposed to be a sub n on the right. So the n rows are still the same n rows you had before with A, but now you're going to augment that with the n rows of I sub n on the left, so that gives you 2n columns, n rows, 2n columns. Okay? Okay, on the right, to obtain this matrix here. Okay? Bracket A space I, close bracket. That's the augmented matrix AI. Okay? This process is called, and we've already said this, adjoining matrix I to matrix A. Okay. Do that first. 2. If possible, now why we say if possible? Always said that A was a square matrix. We didn't say it was an invertible square matrix. So it may not be possible, but if it is possible, row reduce A to I using the elementary row operations on the entire matrix AI the result will be the matrix I A inverse. Now I can't write superscript, so that means A inverse. If this is not possible, then A is non-invertible, and the other word for that is or singular. Okay. Now the third part, not absolutely necessary, but not a bad idea. Check your work by multiplying to see that A A inverse, I can't write superscript, so that's supposed to be superscript, is equal to A inverse, and that's supposed to be superscript 2 times A, and they wrote it in different order, and both of those are equal to I. They wrote the I in the middle, it doesn't matter. Okay. Let me drag this out so it probably will read a little bit more easily. Okay. Any questions on that? That's how we do it. And it's really a fairly easy process. Just a little bit more than row reduction that we did before, but right there. So linear algebra applied here. They are saying recall Hooke's law, which deals with elastic nature of a material, how you bend or stretch or whatever, and they talk about the flexibility matrix, capital F, that corresponds with the deflection to the force, and if you have multiple dimensions there, you'll have a matrix, and then the inverse of that matrix will be the stiffness matrix, F inverse. And they talk about that. So if you are, say, a mechanical engineer or some other that might be using that, that may remind you of a decent paper topic. Hooke or Hooke's law, both of those would be paper topics as well. Let's see if in the next 5 minutes we can do example 3. Okay? And I want to use that, leave this on the page, but just in case I need more room, let me clear it. Okay? Here is matrix A. Find the inverse of this matrix. By the way, this is also located at larsonlinearalgebra.com. You can see an interactive version of this type of an example. So here's matrix A. And I obviously need to get back to my draw mode. Okay. A is equal to, has to be a square matrix. This is a 3 by 3, so it qualifies. Okay. All right, there's your matrix A. Now, I'm going to skip some steps here because we don't have a lot of time. To find the inverse of that matrix, number one, we don't know if it has an inverse or not. But if it does, we augment that with the identity matrix of the appropriate size, which will be 1, 0, 0, 0, 1, 0, 0, 0, 1. And we start our row reduction. Okay? Well, we want 1 here, we got it. Thank you very much. Okay? We want that to become a 0, so we're going to do minus row 1 plus row 2. That's going to be our first elementary operation, what we're going to do. And that, since we're using the top row, that would be a 1 minus 1, 0, 1, 0, 0. Top row stays the same. Let's add, or let's do the operation. Minus 1 plus 1, of course, is 0. That's what we want it to be. Minus 1 plus 0, minus a minus 1 is 1 plus 0 is 1. Thank you very much. We got a 1 there right where we want it. Minus 1 times 0 is 0, and that gives us a minus 1. Minus 1 times 1 plus 0 will be a minus 1. And minus 0 plus 1 will give us a 1. And minus 0 plus 0 will give us a 0. Okay, next we want this to become a 0. So how we get that to happen? 6 times row 1 plus row 3 is the new row 3. So 6 times 1 is 6, minus 6 is 0. Thank you very much. 6 times minus 6, minus 1 is minus 6, plus 2 is a minus 4. 6 times 0 is 0, plus 3 is 3. 6 times 1 is 6, plus 0 is 6. 6 times 0 is 0 plus 0 is 0, and 6 times 0 is 0 plus 1 is 1. Okay, I'm doing this fast. I hope I'm not making too many dumb mistakes. So we got a 1 here, 0's below it. We got a 1 here, we want 0's above it and below it. Let's take care of the above first, and that will be row 2 plus row 1. Okay, that will make that become a 0. Doesn't mess up this, so we're changing row 1, keeping row 2, so let's write row 2. 0, 1, minus 1, minus 1, 1, 0. Okay, then do it. Add the two together. It gives you a 1. We wanted that to stay. That gives us a 0. That's exactly what we wanted. This gives us a minus 1. That's fine. This gives us a 0. That's good. This gives us a 1, and that gives us a 0. All right, down here we're going to take the row with the leading 1. That's the row 2. 4 times row 2 plus row 3. Okay, so that will be 4 times 0 is 0 plus 0 is 0. Good, we didn't want that to change. 4 times 1 is 4 plus a minus 4 is a 0. We did want that to change to that. 4 times minus 1 is a minus 4 plus 3 is a minus 1. 4 times a minus 1 is minus 4 plus 6 is a 2. 4 times a 1 is 4 plus 0 is 4. And then 4 times 0 is 0 plus 1 is 1. Okay, so let's review what we got. 1 here, 0 is below, 1 here, 0 above and below. We want that to become a 1. How we make that happen is multiply by minus 1. Everything by minus 1, if that would only write. Okay, that's hard to read, but let's see. So now we got that to be a 1. We want 0's above, so basically row 3 plus row 1. Okay, we're using our row 3, so write it down. 0, 0, 1, minus 2, minus 4, minus 1. I hope I wrote it right. Okay, add row 3 to row 1, and you get a 1, a 0, a 0, a minus 2, a minus 3, and a minus 1. I hope I wrote it right. Then we'll add row 3 plus row 2, and that will wipe that one out. So you get a 0, 1, 0, negative 3, negative 3, negative 1. Okay, that our contention is negative 2, negative 3, negative 1, negative 3, negative 3, negative 1, and negative 2, negative 4, negative 1 should be the inverse of the one we had to begin with. Now that's a bit suspicious, but let's see. Negative 2, negative 3, negative 1, negative 3, negative 3, negative 1, negative 2, negative 4, negative 1. Yes, it is. Now, what we don't have time to do is confirm it. We should take that original A here, right here, multiply it by this one, and we should get the identity matrix. We don't have time to do that now. Do you think we need to do it next time, or do you want to just do that on your own? Miguel, you're the Jesus, you determine. You're all that's left. Do it next time. So we'll do that. We won't go back and derive it, but we will verify that next time. And I think that's the only mark I have on this page, so I don't have to erase anything. Homework exercises here. in 2.3 would be any of the odds 1 through 5. They should be all in the back of the book and at Calc Chat. And then finding the inverse of a matrix, I know you can do 7, 9, 11, 13, 15, 17, 19, maybe even 21 and 23. Hold off and we'll do the rest of those next time. Okay? So, any questions?
Did you see my email I sent you yesterday? Because I couldn't get into class.
Oh, really?
Yeah, I was trying and trying. I couldn't get into class.
I,
Calculus 1.
oh, that happens. I don't know why. You did use the right code for the class, right?
Mm-hmm.
Okay.
I even went back to check on Blackboard just in case to see if you could get something new.
I have no idea why. I don't know if it's Zoom. I don't know whose fault it is, but other people were here. In fact, half the class was here and half was not. No, in Cal 1. You were the only one. No, wait. Cal 3, right?
Yep.
Yeah, Cal 3. Yeah, half the class was here and half wasn't. It may be the other 3 students who weren't here also were having that problem. I was so amazed that many people were absent because that class usually is much better attended. It is out there on YouTube video now under the playlist, so you can go to week 1 instructional, whatever it is, instructional something another thing. It's the second thing under week 1, and you can find the link to the YouTube videos, and then go for the one that deals with, well, the last one at the bottom of the page of the list. That will be the one from last time. Sorry about that. I have no idea why sometimes it works and sometimes it doesn't. I've had people in several other classes tell me the same things happen to them, and I cannot figure out why. I have 20 some people in some class, and this one person say I couldn't get in, and for a while I was wondering if he was just, well, one of them was doing something wrong. He was trying to use the same code he had previously, and the codes change every day, so I change them every day because some people hack, and the hackers can get in and mess up your class. So if you use the same one over and over and over, someone will figure it out and come in and start messing with your class. Sometimes they put pornography in the background or other things like this, and it's just a real pain. So I change codes every day. So that's a little bit of a pain, but it's not as big a pain if someone's hacking it. So sorry that happened, but it's out there. That's why I record the classes. It's out there on YouTube video now. All right. Okay, well then have a good weekend. We will see you Monday in Cal 3 again and linear algebra again. All right, take care. And here we go. Now, linear algebra, were you here? I mean, differential equations. Same thing happened there, or were you?
Yep.
It did.
I tried, and it was like, I don't know if it's my Zoom, so
Yeah.
I sent you a screenshot of what it showed me on the screen.
Okay. Well, no, I haven't seen emails because we've been out of town twice this week, and I'm just way behind on emails. So I'm going to try to catch up tomorrow.
Okay.
All right. Take care. Have a good weekend. Work. All right. Bye-bye. Just going to stop the sharing and end the meeting. Bye-bye.